So we studied this Sturm-Liouville problem. The equation is classical, Sturm-Liouville equation. The first boundary condition is also classical, but the second boundary condition is unusual. It contains a parameter on both sides. On the left side, A lambda plus B, and on the right side, C lambda plus B. That's why we call it linear, because lambda is contained here linear. A, B, C, D are real constants. We consider the case AD minus BC less than 0. Lambda is the spectral parameter. Qx is real valued and continuous function over the interval 0, 1. Little bit history of the problem. The case AD minus BC greater than 0 was studied in many papers. I can mention Fulton's paper in Proceedings of Royal Society of Edinburgh from 1977, where you can find more references and connections with applications. So this problem appears in many real-life situations, engineering problems, physics problems, even probability. Fulton considered this case, AD minus BC greater than 0, using exit spaces with indefinite metric. It is also called Punter-Yagub space, and using this indefinite metric, it is proved that there is self-adjoint operator associated that problem, and then basis properties follow from here. Kerimov and Mirzoyev in 2003 considered the same problem, Siberian Math Journal, but the approach was different. Instead of exit spaces, instead of Punter-Yagub space with indefinite metric, this paper from 2003, they studied the problem directly using asymptotic formula of the eigenfunctions, which comes from asymptotic formula for the eigenvalues. Biorthogonal system are explicitly defined, explicitly constructed, and then using quadratic closeness, I will tell more about this method in coming slides, and using quadratic closeness, Barry's theorem proved basis. Note that here, this case was studied, AD minus BC greater than 0. In this case, there are no complex eigenvalues, there are no multiple eigenvalues. All the eigenvalues are simple, real, so problem is considerably simpler in this case. The case AD minus BC less than 0 is much harder. In this case, it is possible that the problem has multiple eigenvalues, complex eigenvalues. This problem was studied by Aliyev in 2010. This is different author. It is not me. But they used again Punter-Yagub space, indefinite metric, exit spaces for this for their paper. In general, Sturm-Liouville problems with eigenparameters in their boundary conditions, in general form, were studied before by Rusakovsky and Shkalkov. They obtained results about completeness of the root function system and other related properties, using again very recently, Professor Shkalkov returned to this topic and studied particular case of the type that I have shown you, with linear dependence. In particular, Professor Shkalkov looked at this special case when our boundary condition, first boundary condition, is replaced by this simple case. and he obtained some results. The results that I will show you are in perfect agreement with the results of Professor Shkalkov. Again, Professor Shkalkov used exit spaces for the eigenspace, indefinite metric associated with it. Note that the problem studied by Professor Shkalkov is special. First boundary condition is y prime 0 equals 0. Now, coming back to our problem, you remember it is formed. It is proved by Binding and Brown that that particular problem can have only 4 cases. All the eigenvalues are simple. All eigenvalues are real except for a single eigenvalue of algebraic multiplicity 2 are simple. We call this double eigenvalue case. All eigenvalues are real and except for a single eigenvalue of algebraic multiplicity 3 are simple. And finally, all eigenvalues are simple apart from one conjugate pair of non-real eigenvalues. They are all real. The asymptotic formula are obtained for much more general problems by, again, Binding Brown, Watson in 2004 for general rational dependence on lambda. In the particular case of linear dependence, the asymptotic formula like this. So the method of going from asymptotic formula to the quadratic closeness to trigonometric systems, this method was probably first introduced by Kostychenko and Prof in this paper from 1953. So after you prove quadratic closeness, you can use Barry's famous theorem about completeness of minimal system. The method of using the biorthogonal system for the minimality is introduced by Moiseev and Kapustin, for example, in this paper, and it is references find similar approach. The difference is that in the problems of Moiseev and Kapustin, special problems considered when Q exceeds 0 and the boundary conditions are very special. So motivation of the current work generalize the cases considered before. So the case A equals 0 when lambda was present only on one side, or C equals 0 on the other side. These were considered before in 2007 by me, again in 2021 by me. Let us introduce some notations. So we say Yn is an eigenfunction if it satisfies the equation for lambda equals lambda n. As usual, we denote scalar product by this symbol and norm by this symbol. So before presenting our results, we need to find inner product of eigenfunctions. In contrast to the previous papers, my papers and other authors' papers, this problem is the case that we consider is harder because there are always at least two cases. For example, in this lemma, we have two cases when lambda is different from minus d over c, when one of them is equal to minus d over c. Both of them cannot be because they assume that lambda and n are different from lambda. So in all the lemmas and the formulas that you will see in the following slides, we need to consider several cases. This was not the case in the previous problem. This is the difficulty of this problem. Several cases needed to be considered in each case or each formula. So the norms of the eigenfunctions corresponding to complex non-real eigenvalues is calculated. There are no cases in this because minus d over c is a real number, so lambda r cannot be equal to minus d over c. So there is only one case in this form. So the first associated function is defined like this. As you can see, it looks very similar to the formula of it looks very similar to the given equations. The only difference here is plus yk. And here, the second boundary condition is also different. Okay? This definition of the first associated function comes from Neymark's definition, classical differential approach. We note that associated function of the first order is not unique. If you take associated function, first order, and add cyk, you get again an associated function. So there are many of them. This will be crucial in the coming slides. So using this first order associated function, we can calculate norms of the eigenfunctions. Surprisingly, to find the norm of the eigenfunction, you need to use the associated function of the order. And we introduced this notation, Bn. It is important that Bn is not equal to 0 because it will appear in the denominators in the coming slides. This lemma proves this. Also, we need to find sometimes inner product of eigenfunctions corresponding to complex non-real eigenvalues. If, as you know, in this kind of problems, non-real eigenvalues appear in pairs. If lambda s is an eigenvalue, its conjugate is also eigen. So ys and ys are conjugates of each other. So their inner product satisfies this relationship. Again, this symbols ts, tr will be important because they will appear in the denominator and they need to be non-zero, which we using the definition of first associated function, we can find it is inner product with ordinary eigenfunctions. As you can see, several cases are possible here. That's what makes this problem harder. Lambda k, which is multiple eigenvalue, is different from minus d over c. Lambda n is also different from minus d over c. When one of them is equal to minus d over c, formula also change. If lambda k is an eigenvalue of multiplicity 2, but not 3, then we can introduce this symbol tk, which will appear in the denominator soon. And yk, the inner product of yk plus 1 and yk, the associated function and the eigenfunction can be determined using this formula. Now we can jump to second associated function. Again, we use Neymark definition for the second associated function. It comes from that book. We again note that, as you can see from this definition, second associated function is determined using the first associated function, which was already defined before. It is important to note that as yk plus 1, yk plus 2 is not unique. There are many of them. If yk plus 2 is second order associated function, and you add d multiplied by yk, the eigenfunction, you again get a second associated function. Also, it is important to note that when you change yk plus 1, the previous associated function, to yk plus 1 plus tyk, automatically your second associated function also changes to yk plus 2 plus c times yk plus 2. Okay, we have the definition of yk plus 2, the second order associated function. We can find inner product of yk plus 2 with other eigenfunctions. Several cases again are possible when they are equal to critical value minus d over c, when they are not equal minus d over c. We can also find inner product of the first associated function with the eigenfunction. Surprisingly, we need to know second associated function to find the formula that you see here. So we need to know yk plus 2 to find inner product of yk plus 1 and yk the first associated function and the eigenfunction. Several cases again are cancelled. Here in this formula, we see inner product of second associated function and the eigenfunction. As you can see, there is a non-zero term here, for which we can prove that it is always different from zero. Actually, it is possible to prove that it's greater than zero, but it is not important. So when lambda k is equal to that critical value minus d over c, all the formula, as you can see, change. Now we will introduce several functions which will be crucial for the presentation of the data results. Call them special associated functions, yk plus 1 star and yk plus 1 ds. So this, as we said, there are many associated functions, but one of them is, some of them are very important. There is yk plus 1 star, such that it satisfies this equality, this simple equality. Yk plus 1 star multiplied by yk plus 1, net product is equal to this. There is only one such function. Similarly, in the case when lambda k is equal to that critical value minus d over c, we can state the same result. Similarly, if there is special function yk plus 1 ds, which has similar property when it is multiplied by the second associated function. Again, the case lambda k is different from minus d over c, and the case when lambda k is equal to minus d over c are standard set. And existence of special functions yk plus 2 star and yk plus 2 ds. Yk plus 2 star is defined simply. We use that same constant from the previous. Yk plus 2 ds is defined by this equivalence. The case lambda k equals minus d over c. Finally, we are ready to state our results. To reduce the number of cases, I introduced these notations. Unfortunately, I understood this later in the middle of the paper. So perhaps these notations could be introduced earlier to reduce the number of cases from the beginning. So to reduce the number of cases, let's just introduce this symbol. This Gothic letter A means this if lambda is different from minus 2 over c, this if lambda is equal to minus 2 over c. We can introduce similar notations for the associated functions and even for special associated functions, yk plus 1 star and yk plus 1 is yk plus 2 d star and yk plus 2 is. Introduction of these symbols will make our coming formula very simple. So here is the system of functions yn when one of the function is removed corresponding to arbitrary integer, non-negative integer n. This is a basis. How do we prove it? First, we introduce the biorthogonal system using this notation. 1 over bn, bn is non-zero. That's why we prove it in lemma. And then this symbol in the denominator, which can also be proved, is non-zero. This is determinant. Ynx is the function in the system. Ylx is that removed function, which we use for the biorthogonal system. So in this case, the basis is, the system is always a basis in zero. Case 2, when there is a double eigenvalue. In this case, if you remove the associated function corresponding to that eigenvalue, then the system is basis. The biorthogonal system is defined by this equivalence. But if you remove the eigenfunction corresponding to double eigenvalue, but keep the associated function, the system is not always this. There is a necessary and sufficient condition. And this necessary and sufficient condition is stated using that special function, yk plus 1 star. The biorthogonal system appears here. As you can see, it is important that that denominator is different from 0. Otherwise, it will not be a biorthogonal system. It will be undefined. If you keep both of the functions, the associated function and the eigenfunction, but remove some other function, then it is always basis. As you can see, there is no condition in this case. Now, case 3, when there is a double eigenvalue. In this case, if you remove the second associated function, then it is always a basis. The biorthogonal system is defined here. This was also noted by Professor Shkalikov in his 2019 paper in differential equations, that when you remove second associated function, but you keep the first associated function and the eigenfunction, the basis. But when you remove the first associated function, keep the second associated function and the eigenfunctions, then it is not always basis. There is a necessary sufficient condition. The biorthogonal system is defined as in this form. The results of Professor Shkalikov are about that special case y prime 0 equals 0. We consider more general. If you remove the eigenfunction corresponding to the multiple eigenvalue, but keep. So if you keep the eigenfunction corresponding to the first associated first, the eigenfunction corresponding to the multiple eigenvalue, it is first and second associated. You keep all of them in the system, but remove some other eigenfunction corresponding to L, then it is always a basis. This perfectly agrees with the results obtained by Mr. Shkalikov for the special case. Of course, there is also the case of complex eigenvalues. There can be only two complex eigenvalues, and they are conjugates of each other. One needs to consider the cases when you remove an eigenfunction corresponding to a complex eigenvalue, or you remove an eigenfunction not corresponding to complex eigenvalue, only corresponding to real ones. Both of these cases are considered here, and the biorthogonal systems are constructed. I also looked at two special examples. It was not easy to find these examples. I tried to find examples to both cases when lambda k, which is multiple eigenvalue, corresponds to minus d over c, and when it is different from minus d over c. Here, I have a triple eigenvalue in this problem, which is different from minus d over c. And then all the results obtained for the triple eigenvalue are checked for this particular. This example, 0 is a triple eigenvalue, and it is equal to minus d over c. When we started this research, I didn't even know if such cases existed. So I didn't know if there can be a triple eigenvalue equal to minus d over c. I even tried to prove it cannot happen, but I failed and then found these examples. Again, in these cases, we verified the results for this particular problem. I think I can stop here. Thank you.